Let's study 10th standard ICSE chemistry, chapter 7b, ammonia. Ammonia is a basic gas. The lab method for preparing ammonia is by heating a mixture of some ammonium salt like ammonium chloride with an alkali like calcium hydroxide. If you look at the equation, we see in the presence of heat, a salt is produced, water vapor as well, and we get the ammonia gas as required. You can see here that a less volatile base is displacing a more volatile base in this reaction. By the way, ammonia when dissolved in water forms ammonium hydroxide, which is a weak alkali. These reactions were also present in the chapter 3a, acids, bases and salts, and this was used as a test for the hydroxyl ions. For lab, we prefer calcium hydroxide, not sodium hydroxide, because sodium hydroxide and even potassium hydroxide are deliquescent, whereas calcium hydroxide isn't, and it's cheap as well. As we know, the ammonia gas produced has moisture as well. So how to get rid of it? We should use a drying agent. Kong sulfuric acid is ruled out because acid will react with the base. We need something which won't react with ammonia. So let's use a basic dry agent, calcium oxide, also called quicklime. So we get dry gas here. And it is being collected by downward displacement of air. So initially, this tube was filled with air, but as ammonia is getting collected, the air is being pushed out of it. So in the end, it will entirely be filled with ammonia gas. Clearly, that is because ammonia gas is lighter than air. We can't collect it over water because ammonia gas, just like HCl, is highly soluble in water. Even ammonia gas can give us the fountain experiment. Now the ratio of ammonium chloride to calcium hydroxide in the round bottom flask is 2:3. Calcium hydroxide is also called slaked lime, whereas ammonium chloride is called sal ammoniac. When slaked lime is dissolved in water, and it is only slightly soluble in water, it is called lime water. Now there are a few precautions which we need to keep in mind. First of all, the reactants should be in finely powdered form so that there is maximum surface area for reactions. Make sure that the slaked lime used is in a higher ratio compared to ammonium chloride. That's because ammonium chloride is a sublimatory substance, so it may sublimate. So to counteract that, we need to have a greater quantity of calcium hydroxide. The salt we are using is ammonium chloride. Even ammonium sulfate can be used, but not ammonium nitrate, because ammonium nitrate is very explosive in nature and it may decompose to form nitrous oxide and water vapor, which is something we don't need. Also, if you notice in the diagram, this neck of the round bottom flask is inclined downwards. This is so that the water vapor, most of the water vapor being released, should simply trickle back down into the flask, and very less moisture should continue their journey with ammonia, and that too will be taken care of by the drying agent. Now how can we be sure that this is ammonia gas? Well, the test for ammonia gas is that when a glass rod dipped in conch HCl is brought near it, dense white fumes are seen. And yes, the dense white fumes are of ammonium chloride, which is a sublimatory substance. Now there is another method of preparing ammonia in the lab using metal nitrides, although it is less preferred because it is not as cheap as the previous method. Here we take a metallic nitride like magnesium nitride. It's quite expensive, but once we have it, then all we need to do is add warm water. When we add warm water, the reaction takes place giving us a precipitate and ammonia gas is released. And as usual, it is dried with calcium oxide and collected by downward displacement of air. Make sure that the lower end of this thistle funnel is dipped in this solution so that the ammonia gas doesn't escape via the thistle funnel and it escapes only via the delivery tube. Now let's talk about the manufacture of ammonia in industries. What we studied earlier was the lab method, but in industries, the method is called Habers Process. In Habers Process, the gases hydrogen and nitrogen are combined together in the ratio 3:1 by volume, and they react reversibly to give us ammonia. It's an exothermic reaction, but there are some conditions which need to be satisfied. First of all, the temperature has to be 450 to 500 degrees Celsius. The pressure should be 200 to 900 atmospheres. Catalyst is used as well as a promoter. Promoter will increase the efficiency of the catalyst, and catalyst will increase the rate of reaction. This reaction is reversible. That means the ammonia can once again decompose to give hydrogen and nitrogen gas. Also, we see that totally 4 volumes of gases are combining to give you just 2 volumes. So here, Le Chatelier's principle will be used. One precaution to keep in mind is that the hydrogen and nitrogen gases used may have impurities like carbon monoxide, carbon dioxide, and hydrogen sulfide, which may poison, if you can use the term, the catalyst. That is, the catalyst won't work effectively. So make sure that the nitrogen and hydrogen used are pure and free from those impurities. Also, as I said, whatever ammonia is produced may decompose back into hydrogen and nitrogen. So in the end, what we get is a combination of 3 gases, ammonia, as well as some unreacted or decomposed hydrogen and nitrogen. But I want only ammonia. So how do I separate these 2 gases from the third gas? Well, there are 2 ways to do that. One is you can pass them through water. Ammonia is highly soluble in water, but not hydrogen and nitrogen. So the ammonia will be dissolved in water to give you the ammonium hydroxide solution, from which you can get ammonia back easily. This way, hydrogen and nitrogen have been separated from the mixture. Another method is to cool them. You see, the ammonia gas can be easily liquefied, whereas hydrogen and nitrogen become liquid at a very low temperature. So if we cool ammonia, we get liquid ammonia. Liquid ammonia has no water. It is just ammonia in liquid form. This way, hydrogen and nitrogen will continue to be in gaseous state, and they are now separated, which can be reused in the Habers process. Now, since this reaction is exothermic, this means that lower the temperature, more will be the forward reaction. This is true for any reversible reaction which is exothermic. Remember, Le Chatelier's principle states that lower temperature, more of the forward reaction, which is what we want. We don't want the backward reaction much. That is why the temperature is kept at 450 to 500 degrees Celsius. We can't get lower than that because then the rate of reaction itself will become too low. But definitely we should not keep it very high, like 1000 degrees Celsius, because then ammonia would decompose totally into nitrogen and hydrogen. Also, I had mentioned that here 4 volumes of the reactants are giving just 2 volumes of the products. Such a reversible reaction, which proceeds with a decrease in volume, according to Le Chatelier's principle, will favor the forward reaction under a high pressure. So that is why we kept the pressure as 200 to 900 atmospheres, because at such a high pressure, the forward reaction will be favored since the volume is decreasing. But we can't go beyond this, like 1000 or more than 1000 atmospheres, because then the machines and the production plant may not be able to withstand such high pressures. So we have to take the optimum values, and these are the optimum values. The physical properties of ammonia are it's colorless, strong pungent smell. Pungent means strong, irritating. It is slightly alkaline, that is bitter to taste. It is lighter than air, of course, and it is highly soluble in water, which can be proved by the fountain experiment. Just like in HCl, even ammonia will give us a fountain. So we start with the dropper having water, and there is no water inside. There is no moisture inside the round bottom flask, which is inverted. It is filled with dry ammonia gas, because only dry ammonia gas is highly soluble in water. When you press the dropper, the water enters the neck of this flask. Some of the ammonia gas quickly dissolves in it, creating a partial vacuum. And if there is a partial vacuum, that means there is a pressure drop inside. Comparatively, the outside pressure is greater, and the outside pressure will push this red litmus solution into this tube, which goes up and comes out with pressure. And interestingly, the red litmus paper turns blue because ammonia is basic gas. Now let's talk about the combustibility of ammonia gas. Ammonia gas normally is not combustible, nor does it support combustion, but it can burn with oxygen under special circumstances. First of all, if you have pure oxygen, air has only 21% oxygen, but here it's pure oxygen, then ammonia will burn with a green or greenish yellow flame, and the products formed are nitrogen and moisture. The observation here is green flame. Another way to react it is use dry oxygen and use a catalyst like platinum for the reaction to take place. The products formed are nitric oxide and steam. Steam, by the way, will condense to form water droplets. Nitric oxide, as soon as it comes in contact with the air, It combines with oxygen to give nitrogen dioxide, which is a reddish brown gas, which turns acidified green ferrous sulfate solution brown. So that's the observation here. The temperature should be kept at 800 degrees Celsius. And this is the first process for the Ostwald's process, which we'll study in the nitric acid chapter. Even if we switch off this burner, the platinum will continue to glow for some time because it's an exothermic reaction. So the heat produced will keep the platinum hot. Now, as said earlier, ammonia dissolves in water to give you liquor ammonia, which is also called ammonium hydroxide. But in solution, it always exists in the form of ammonium ions and hydroxyl ions. We have studied this equation in acid, bases and salts chapter as well. Because of the presence of these hydroxyl ions, ammonium hydroxide is an alkali. Because of these hydroxyl ions, the red litmus paper will turn blue and phenolphthalein solution will turn pink. However, this dissociation is not complete. There's only partial dissociation. So the concentration of hydroxyl ions is low. That is why it's a weak alkali. In order to prepare this ammonium hydroxide, again, we could simply dissolve the ammonia gas into water, but then there will be back suction. So just like HCl, even here, we shall use a special funnel arrangement, which will reduce back suction. This is a special funnel arrangement to reduce back suction. Whereas if we just pass the ammonia directly, it will dissolve quickly, and the partial vacuum created here will allow the water to be sucked in, and it may damage the apparatus. So just like HCl gas, even ammonia gas can be dissolved in water by the special funnel arrangement, which reduces the back suction as well as increases the surface area for absorption. Also, a very saturated solution of ammonia in water is called liquor ammonia fortis. Fortis simply means saturated. Remember, when ammonia dissolves in water, then only we have hydroxyl ions available for the alkaline properties like turning red litmus blue. If you have dry ammonia gas, that won't turn red litmus blue because there are no hydroxyl ions present. So you may need to use moist litmus paper to test ammonia gas's basicity. And if you condense it into liquid ammonia, I'm not saying liquor ammonia, liquid ammonia which has no water, even that will not turn red litmus blue. Next, ammonium salts. Ammonia reacts with the acids to give the respective salts. On the other hand, ammonium hydroxide neutralizes these acids to form salt and water only. This is a neutralization reaction. When you heat ammonium chloride, it decomposes to form ammonia and hydrogen chloride gas. This is called thermal dissociation because it's reversible. And remember, ammonia becomes ammonium when dissolved in water because the water splits into hydrogen and hydroxyl ions as we have studied in chapter 3a, and the hydrogen, that is a proton, is attached to the lone pair of electrons on nitrogen to form the ammonium ion. Now, one property of ammonium hydroxide which is very useful is that, just like sodium hydroxide, even it reacts with metallic salts to give colored precipitates with different solubility. We have studied this in 3b analytical chemistry, and this is also there in chapter 9 practical chemistry. For example, ferrous salts, ferrous sulfate, ferrous chloride, etc., reacts with ammonium hydroxide to give a dirty green precipitate. So this helps us to identify the metallic ions. And this precipitate is insoluble even in excess of ammonium hydroxide. Ferric salts give reddish brown precipitate. Lead salts give chalky white precipitate, insoluble in excess. Zinc salts also give white precipitate, but they are soluble in excess of ammonium hydroxide. So ammonium hydroxide can be used to distinguish between these salts. Copper salts will give pale blue precipitate in ammonium hydroxide, but again it is soluble in excess because in excess it reacts with the ammonium sulfate formed here and the ammonium hydroxide which is in excess to form a complex salt called tetraamine copper sulfate, which is soluble. So the whole solution then becomes blue. Now let's understand the reducing action of ammonia gas. Ammonia gas is a strong reducing agent, which can be proved by this experiment. If you have some metallic oxide like lead oxide or copper oxide and you heat it with dry ammonia gas, you can get the pure metal. Ammonia will snatch away the oxygen. The reaction is this. You can get pure metal. So you can see that the oxides have been reduced to the metals. Losing of oxygen is called reduction. Hence ammonia is called the reducing agent because it reduces metallic oxides. The observation here is that the black copper oxide has now given us a residue which is pinkish brown in color. Lead oxide, well, it was buff yellow when it is hot. It gives us a grayish metal at the end. And of course, moisture is released and nitrogen gas is released as well. The moisture can be collected in this U-tube by condensation, and nitrogen gas is collected by downward displacement of water because it is hardly soluble in water. Another equation to prove ammonia gas is reducing action is its reaction with chlorine. Now, if ammonia is in excess, then the final product will be ammonium chloride and nitrogen. That's the net reaction. Of course, it happens in steps. So here the observation is that dense white fumes will be seen. But if chlorine is in excess, then a completely different product is formed called nitrogen trichloride, which is a greenish yellow liquid. It is an explosive liquid. And of course, HCl gas is released, which will give dense white fumes, and a glass rod dipped in ammonium hydroxide is brought near it. Now let's talk about tests for ammonia. Of course, it's basic, so it changes the color of the indicators as normal, but that's not a chemical test. The chemical test would be either with the glass rod, which we've already discussed, similar to the test for HCl, or we can pass the gas through a copper sulfate solution. If it's ammonium hydroxide, then initially you'll get a pale blue precipitate, but with excess of ammonium hydroxide, it will turn into a blue solution because this precipitate will form a complex salt and it will dissolve in the solution. One more test for ammonia gas is to pass it through Nessler's reagent. Nessler's reagent turns brown or gives a brown precipitate when there is ammonia passed through it. Now let's study the uses of ammonia gas. We can get many synthetic products from it like hydrogen, nitric acid. I had mentioned that it is used in the Ostwald's process, which we'll study later. It is also useful for manufacturing of explosives, especially ammonium nitrate. And that's the reason why we didn't use ammonium nitrate in the lab preparation also. It is useful in fertilizers like urea, ammonium sulfate, and ammonium nitrate. So interestingly, this fertilizer can be used as an explosive as well. Some ammonium compounds like ammonium carbonate is a constituent of smelling salt. That means if somebody has fainted, the doctors use ammonium carbonate because it will quickly dissociate to give you ammonia gas, which has a very pungent odor, and the fainted person would wake up. But if you don't have ammonium carbonate, you can use your socks as well. Ammonium chloride, well, it dissociates to give ammonia gas and HCl, and HCl helps in pickling of metals. You see, when a metal has to be galvanized, that is coated with zinc to prevent rusting, first of all, we should remove the metallic oxide coating on top of it. For that, we use HCl because HCl will remove the coating, exposing the metal part, and then we can galvanize it. This was mentioned in HCl chapter also. Also, ammonium chloride is used in dry cells as a constituent of the electrolyte inside it. Now, ammonium sulfate is a fertilizer and to manufacture alum, which is a chemical. Now, the uses of liquor ammonia and liquid ammonia. Remember, liquor ammonia is ammonium hydroxide, that is ammonia dissolved in water. It's an aqueous solution. Whereas liquid ammonia has no water. It is pure ammonia which is condensed at a low temperature. Liquor ammonia is used as a cleansing agent because it emulsifies, that is dissolves the fats and grease. So it is used for dry cleaning. Liquid ammonia is used as a refrigerant because it is highly volatile and it is high latent heat of evaporation, and also because it easily liquefies under pressure at low temperature. In a refrigerant machine, like in the refrigerator, electricity is used for ammonia to be converted into a liquid inside the tubes. When this ammonia becomes a gas, it will absorb a lot of latent heat of evaporation. Thus, it cools the surroundings very quickly. Earlier, CFCs were used, chlorofluorocarbons were used as a refrigeration gas in ACs as well. But when scientists discovered the ill effects of CFCs, that is, they cause ozone holes, now CFCs have been replaced with ammonia.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.